Swayam Prabha. Digital India. Educated India.
Welcome friends, this is the 9th class on GPS surveying. Today I am going to discuss on GPS observables. As I told you in the last class that GPS observables are required to get the ranging information of the satellites from the receiver. So this is the most important parameter required to determine the position of a receiver. Now these observables are sometimes associated with also some errors. So today's class I am going to discuss on, in the beginning I will like to discuss on GPS observables, its types, and then the errors that the GPS observables carry with, and finally because the quality of the GPS surveying will depend upon the quality of GPS observables, so we need to test the quality of GPS observables. So I will like to discuss on it using 3 parameters: URA means user range accuracy, user range errors, and satellite geometry. Now what is GPS observable? Or GPS observables are the parameters which are available from GPS signal, and basically these are the parameters that is we get from GPS signal, and there are 2 types of GPS observables that we are interested specifically for GPS positioning, that is code pseudo range and phase observable. Now these 2 observables are based on from which part of the signal they are being derived from. Like as the name itself says that the code pseudo range are the range of satellites from GPS satellite to GPS receiver, that is find out from the code information of the signal, and phase observable is from the phase of the signal. Now these either the code pseudo range or code pseudo range followed by phase range, these 2 are made use to find out the GPS position. Now the code pseudo range is always the first parameter which is used to find out the position of a GPS receiver, and that is quite approximate, and that is the first thing we need to determine, and subsequently for precise estimation of position we need to go for making use of phase observables. However, since these observables are we receive or we get from GPS signal and GPS signal measurement, and the measurements are always associated or fraught with errors, so these observables are also having some errors which we need to know in detail, so that those errors can be removed from the observables and we end up with more accurate or precise position. Now let me discuss on code pseudo range. As the name itself tells, code pseudo range is determined by measuring the time of transmission from satellite to receiver from the code information available in the signal and the velocity of transmission of the signal from satellite to receiver. So it is the time of transmission of GPS signal multiplied by the velocity of transmission of GPS signal. Now this provides us the range. Now when the time of transmission of the GPS signal is measured from code part of the GPS signal, then it is the code range, and also this. Now you can see this, that means there are two parameters we need which is involved in range computation. So this measurement of these parameters involve some errors, and also there is a lack in synchronization between the satellite clock and receiver clock. So due to this, primarily due to this and due to other factors, there will be large errors. So the range which we will get really from the GPS observable, that is called not the actual range but the pseudo range. So it is measured from using code, so code pseudo range, this is actually this is available with us. Available from GPS signal as observable. So in subsequently we need to process these observables to find out the actual range. So actually code pseudo range is equal to geometric range plus so code pseudo range that we get from GPS signal, it is a, there is the geometric range, that means actual range, plus the error due to time synchronization plus other error. So this is what is our GPS code observable. This will consist of these three parts. So we need to know these errors and we have to remove this thing, and after removing this thing we have to determine this time synchronization error, and once we know this thing, then from this and this we will be able to find out the position correctly. This is the idea. Next observable, the other type of observable is carrier phase observable. Basically carrier phase observable is the difference in phase between the signal that is transmitted by the satellite at the instant of its transmission and the instant of its reception at the receiver. So we will find that there is a phase at the time of transmission, say phi t, and there is a phase, suppose at the time of reception. So the difference between these two is what is carrier phase, but this also includes plus number of full cycles that the signal travels during transmission to reception. So if we see, like this is suppose the satellite and this is the receiver. So what is there? So we can see that is a phase transmission and the phase reception, but in between these two phases there will be, suppose this is the, now I can see here that is the difference between the transmission and reception, but apart from that there will be full numbers of cycles. So like that there will be full numbers of cycles. So the carrier phase observable fundamentally consists of the difference in phase between the transmitted between of the signal at that instant of transmission and that at the time of reception plus full numbers of cycles. Now for this actually GPS receiver counts the, actually measures the phase at the time of transmission as well as at the time of reception, as well as it keeps the counts the full number of cycles that it transmit, that it receives between two consecutive epoch, but the receiver will not be able to register the full number of cycles that the signal has travelled before the first epoch of observation. So always there will be a number, an integer number n, which will be associated with the carrier phase measurement observable, which is not known for the user, and that is known as integer ambiguity. So in case of phase measurement there is another parameter which is coming, which is not known, and apart, so we may end up with a relation like this: carrier phase observable will be equal to an geometric range plus integer ambiguity plus fractional phase difference plus errors. Now though we have found that the errors are present both in case of pseudo range measurements as well as carrier phase observable, but the amount of errors in carrier phase observable will be different from that available in pseudo range. That is one thing has to be mentioned or to be marked, that the amount of error that will be available along with the observables are defined for different types of code as well as defined for different types of carrier. So as we know, we have different types of code like CA code, P code, etc. So the errors will be defined in this case. Similarly, we have L1, L2, L5 carrier frequency. For them also errors will be error 1, error 2, error 3, something like that. So we see that both the observables are fraught with errors, and since the GPS position will depend on the GPS observables, so this observable should be free from those errors, otherwise our position determination from those observables will also be associated with some errors. So I will now discuss about errors. Errors in GPS observables. The errors in GPS observables arises out of defined sources, defined reasons. However, from the nature of the errors, we do classify the errors under 3 categories. Number 1, gross error. Number 2, systematic error. And number 3, random error. Now, gross errors are the errors, or sometimes we say it as a mistakes, that is caused due to undesirable condition, as well as it depends also on persons who is taking the GPS data, or also maybe due to some other reasons which is not seen to the observer. However, these errors need to be removed immediately after collection of GPS data. So of course, before removing, we need to identify whether our data is associated with a gross error or not, and if their data is associated with gross error, then we had to remove those errors. Now, what are the sources of gross errors? The most important and widely prevalent gross error is due to the physical obstruction of the signal as it is received from satellite, because many times we will see that our signal may not get clear sky, they may be interrupted by some trees, or it may be there may be some birds which are flying, so the signal may be disturbed by them, or there may be some aeroplanes, so or many other way how it can be there. That means physical obstruction of signal during its transmission from satellite to receiver. Due to that, there may be some gross error. Another important source is that interference of the signal, because GPS signal is electromagnetic in nature, and there may be some electromagnetic field in the field like transformer, there may be high tension line, or there may be ionospheric activity in the atmosphere. So all those may cause some interference in the GPS signal, which may lead to some gross error. Apart from that, the observer may not take care to set up the instrument exactly on the station, or it may not be leveled properly, or the measurement like height of instrument measurements, all those things may not be taken properly. Sometimes there may be instability in the station occupation. So all these causes gross errors in the data. So the how we can minimize or remove, first thing is that we should plan our GPS observation in such a way that there is enough number of satellites visible during the time of observation. We should give enough cutoff angle. Now what is cutoff angle? So it is the angle which we have to provide to the receiver at the time of receiving the signal, beyond which there will not be any obstruction. So suppose cutoff angle is 15 degree we have given, so we should see in the field that if we take a line having 15 degree from horizontal, there should not be any obstruction like this. So this is cutoff angle. So in that case there will be less possibility to get obstruction. Then another thing we have to see that near the station or observation there should not be any transformer or high tension line, so that there is no interference of the signal. Then before setting up the instrument we should take care that the station is on a stable ground and it has been properly leveled as well as centered properly, and the parameters to be noted down has to be taken properly, like height of the instrument and many other parameters we will be in need, that those has to be noted down properly for subsequent use. So the best way to avoid gross error is to take care before starting our observation. Once the observation is available, then we have to check whether there is any gross errors, then that has to be removed, those data has to be removed from further computation. Next source of errors are systematic errors. Systematic errors are errors which definitely follow some physical rule. So this is specific to the instrument or procedure related. So GPS there may be different types of systematic errors that is present in GPS observation, that may arise out of our satellite space segment, that may be arises out of the during transmission through atmosphere, it may be arises from the receiver, or maybe other way. This in detail I will take up in the next class, but systematic error can be minimized or removed because it follows some physical rules. And the last but not least but also important is the random error, which does not follow any definite rule, so it cannot be modeled and we do not have any control on random error. So that can only be limited by taking proper care during planning and execution of the surveying, and later after removing the gross error and systematic error when the data will be processed, then we should check about the random error. If it is available, then statistically we have to adjust the error among different parameters so that the effect on position gets minimized. So whatever it is, so these errors will be available. So with these errors, so we can say that the observable equations we find like this: for pseudo range it is the geometric range, then it is the error due to your receiver clock error, error due to satellite clock error, ionospheric error, tropospheric error, receiver satellite hardware error, then this is multipath error, then it is the random error. So we can say that the pseudo range consists of so many parts, like geometric, this is the thing which we really looking for, but there are so many errors which we have to reduce or minimize or reduce or take out. Similarly, carrier phase is also having these parameters like an additional parameter, this one that is called integer ambiguity parameter. But though I am using the same symbols, the amount of error, those will be associated with code pseudo range observables, and those in the phase observables will not be the same. Anyway, so ultimately the quality of the GPS observable will depend on what is the amount of error that is available in the observable. So now I will talk on quality of GPS observable. So how to, so the quality of the GPS observable will depend upon what is the amount of error that is it has. The errors that will be available in the GPS observable, already I had told you different sources. Apart from that, there may be error due to earth and relativistic effect, due to the geometry of the satellites with respect to the receiver, then the models that we will use for to remove the errors may be very simple enough, which does not represent the physical process, so an error may come. So like that there may be different sources. However, we have some parameters by which we can identify what is the quality. Number one, by dilution of precision. Number two, user range accuracy, and thirdly, user range error. So these are the three parameters which we make use to identify the quality of the GPS observable. Now from the name itself, dilution of precision. Now what is that? It is the relation, it is the parameter which defines the geometry of the satellite with respect to the receiver. Like you can see here that when the satellites are here, if we take a receiver, then the vertical line above it, it is called zenith point, and if we have our satellites well spread over this with respect to this line and above the cutoff angle, then this geometry is called good, and in that case we will have a low dop. So good geometry, low dop. So and if these satellites are clustered at some point, some location, then the geometry is called, this is a poor geometry, and our dop value will be high. So when we will take our observation, the controller will provide us the dop value. So if the dop value is low, then we will expect that our observables are of good quality. If the dop value is very high or very high, like 8 or 10, something like that, then we will think that our observables are not of good quality, then we should stop taking our observation. Another parameter which, so in that way during the collection of the data we can control the quality of our observation. Now once the data has been received, so then also we can check about the quality of this by using the parameter called URA. This URA means user range accuracy. This parameter is available in the GPS navigational data, and it is represented by some index which is available in the third word of the navigational data, bits 13 to 16, and this gives us an indication whether our data is good or not. and also there is a parameter which is available in the telemetry world in the at the bit 23. If that bit is represents 1, that indicates that the received signal has an enhanced level of integrity, that means it is a good quality, and if it is 0 then the integrity is poor, that means the quality is not good. So using this also we can have an information about the quality of the GPS observable. Next, another parameter which is most popularly used, that is called URE, user range error. It is a quantitative parameter which we get from the we compute by taking square root of sum of the squares of individual errors. Actually errors are taken as its effects on the range measurement. So what is the error of some particular error, how much it is causing error in the measurement of range measurement. So that is taken. So for each for some parameter, suppose A, B, C, what is the for this parameter what is the error? DA is the error in range measurement, DB is the error in range measurement, DC is the error in range measurement. So user range error will be square root of DA square plus DB square plus DC square. So lower the value, better the quality of the observable. In that way also we may test the quality of GPS observable. With this I want to conclude today's class, but before that I will like to summarize. GPS observables are the most fundamental parameters which we like to measure or we like to take out from GPS signal. There are two types of GPS observables that is available in GPS signal. One is code pseudo range, which we obtain from the code part of the signal, another is the phase observables. So carrier phase observables, that is obtained from the carrier phase of the GPS signal. From these two we do, using pseudo range we do get the code positioning, and from subsequently we use code pseudo range positioning to find out the position using phase pseudo range. These observables are fraught with errors, and these errors has to be removed or minimized before we go for processing, and the quality of the GPS observable will depend on how much errors it is associated with. Lesser the error, better the quality, and that we can judge or we can find out quantitatively using three parameters like DOP, URA and URE, and the most simple and widely available parameter is DOP, which we can check even during our GPS observation, GPS surveying. So during GPS surveying we should take those data when the DOP value is less. Less means it may be 1 or 2, something like that. Of course this value will depend upon the nature of the project. With this I like to conclude today's class. Thank you. See you again in the next class. Next class I will be taking on systematic error in GPS observables. Thank you very much.